Water is life. It's not just a poetic phrase. It's a fundamental truth that has shaped the entire story of human civilization. Before we built cities, before we wrote laws, before we even had governments, we had to solve one critical problem. How we get water to our crops when nature doesn't provide it exactly when and where we need it. This challenge, this simple need to move water from where it is to where we want to be, has driven some of humanity's greatest innovations and determined which societies would thrive and which would struggle to survive. When we look back at the earliest human settlements, there's a pattern that emerges with striking clarity. People didn't just settle anywhere. They settled near water. The great rivers of the ancient world became the birthplaces of civilization precisely because they offered something irreplaceable, a reliable water source. The Tigris and Euphrates in Mesopotamia, the Nile in Egypt, the Indus in South Asia, the Yellow River in China, these weren't just convenient locations. They were the difference between abundance and famine, between staying in one place long enough to build a culture or having to keep moving as a nomadic people following seasonal rains and natural water sources. But here's what made these early civilizations truly remarkable. They didn't just settle near water and hope for the best. They learned to control it, to redirect it, to make it work according to human needs rather than simply accepting what nature provided. This was revolutionary. Think about what it meant for a farmer in ancient Mesopotamia around 6000 BC to dig a channel that brought river water to fields that were otherwise too dry to cultivate. That farmer was fundamentally changing the relationship between humans and their environment. No longer were people entirely at the mercy of rainfall patterns. Now, they could create their own reliability, their own agricultural security. The development of irrigation wasn't just a farming technique. It was a catalyst for everything we think of as civilization. When you can irrigate, you can grow surplus food. When you have surplus food, you can support people who don't farm, artisans, priests, soldiers, administrators, builders. You can develop specialization. You can create cities. You can build monuments and develop writing systems to keep track of increasingly complex societies. Archaeological evidence shows us that the first true cities emerged in precisely those places where irrigation made agriculture reliable and productive enough to support dense populations. In ancient Mesopotamia, between the Tigris and Euphrates rivers, farmers developed extensive networks of canals and ditches. These weren't simple projects. Some of these canals stretched for miles, requiring enormous communal effort to dig and maintain. But the payoff was transformative. Fields that would have been dust without irrigation became fertile and productive. The Sumerians, often credited as one of humanity's first civilizations, owe their success not just to their ingenuity in writing or architecture, but to their mastery of water management. They understood that controlling water meant controlling food, and controlling food meant power and stability. Egypt's story with irrigation followed a different but equally fascinating path. The Nile River provided an almost miraculous natural irrigation system through its annual flooding cycle. Every year, with remarkable predictability, the Nile would overflow its banks, depositing nutrient-rich silt across the floodplains and providing moisture to the soil. Egyptian farmers learned to work with this cycle, developing basin irrigation systems that captured and held floodwater in enclosed areas, allowing it to soak into the soil before draining away. They also built elaborate networks of canals to extend the reach of the Nile's bounty to fields beyond the immediate floodplain. The Greek historian Herodotus famously called Egypt the gift of the Nile, and he wasn't wrong. Egyptian civilization's prosperity and longevity were built on this reliable water source and the irrigation systems that maximize its benefits. The Indus Valley civilization, flourishing around 2500 BC in what is now Pakistan and northwestern India, developed sophisticated urban planning that included careful water management. Archaeological excavations have revealed wells, drainage systems, and evidence of irrigation networks that supported agriculture in a region where rainfall was often insufficient and unpredictable. These ancient engineers understood principles of hydrology that wouldn't be formally codified for thousands of years, yet they applied them with impressive effectiveness. What's truly remarkable about these early irrigation systems is that they worked with the simplest technology imaginable, gravity. Ancient farmers didn't have pumps or motors or electricity. They had observation, patience, and an understanding of how water, naturally behaves. Water flows downhill. This basic principle of physics became the foundation of irrigation technology for thousands of years. By carefully surveying land and understanding elevation changes, farmers could position their canals and ditches so that water would flow from rivers or reservoirs to fields without requiring any mechanical assistance. This gravity-based approach to irrigation required remarkable precision in planning and construction. Canals had to be dug at exactly the right gradient. Too steep and water would flow too fast, causing erosion. Too shallow and water would pool and stagnate rather than flowing where it was needed. In flat terrain, achieving the right slope might mean excavating channels over enormous distances to gain just a few feet of elevation difference. Ancient surveyors developed ingenious techniques, using basic tools to ensure their water channels would function properly. In ancient Egypt, builders used a tool called a merkit, essentially an early form of plumb line and sighting instrument, to help establish level lines and gradients for irrigation works. The seasonal flooding that characterized rivers like the Nile created both opportunities and challenges for early irrigators. Unlike modern irrigation, which could be turned on and off at will, flood-based systems operated on nature's schedule. The Nile's annual flood typically occurred from June through September, driven by heavy rains in the Ethiopian highlands far upstream. Egyptian farmers had to organize their entire agricultural calendar around this cycle. They grew crops during the cooler months after the flood receded, harvesting before the next flood cycle began. This predictability was a tremendous advantage. Farmers could plan years in advance with reasonable confidence about when water would arrive, but also meant rigid constraints on what could be grown and when. Other rivers were less predictable than the Nile. The Tigris and Euphrates, while generally flooding in spring due to snowmelt in the mountains of modern Turkey, could vary significantly in timing and intensity from year to year. This unpredictability meant that Mesopotamian irrigation required more active management, more elaborate storage systems, and more sophisticated distribution networks to capture water during floods and preserve it for use throughout the growing season. The challenge of managing these variable water sources contributed to the development of complex administrative systems. Somebody had to decide how to allocate water, maintain canals, and resolve disputes between upstream and downstream users. Managing these early irrigation systems was extraordinarily labor-intensive. Imagine the work required to dig a canal miles long, using nothing but human muscle power and simple tools. Wooden spades, stone picks, baskets for moving earth. Thousands of workers might be mobilized for such projects, often during seasons when field work was less demanding. But the labor didn't end once the canal was dug. Irrigation channels require constant maintenance. They fill with sediment that must be cleared. Banks erode and need repair. Vegetation grows and must be removed to prevent blockages. In agricultural societies, a significant portion of the population's work time was devoted not to growing crops directly, but to maintaining the water systems that made growing crops possible. Animals played a crucial role in this labor-intensive approach to irrigation. Oxen and water buffalo were used not just for plowing, but for tasks like operating simple lifting devices to raise water from rivers or wells to higher ground. In many parts of the ancient world, farmers used devices like the shaduf, a counterweight lever system where a bucket on one end could be dipped into water and then raised with less effort than pure lifting would require. Operating these devices hour after hour, day after day, was backbreaking work, often performed by humans but sometimes assisted by animal power. The water wheel, or noria, represented a major advancement. Animals walking in circles could drive a wheel that continuously lifted water from a river into an aqueduct or canal. These devices allowed for more sustained irrigation of fields that were above the level of the water source. Despite the impressive engineering of these early systems, they were inherently inefficient by modern standards. Open canals and ditches lose tremendous amounts of water to evaporation, especially in hot, dry climates where irrigation is most needed. In the intense sun of a Mesopotamian or Egyptian summer, water exposed in open channels can lose significant volume before it ever reaches the fields where it intended. Additionally, these systems suffered from seepage, water soaking into ground along the canal route rather than staying confined to the channel. Runoff was another major source of loss, with water flowing beyond the intended irrigation area or draining away before it could be absorbed by crop root zones. These inefficiencies meant that ancient irrigation required far more water to be diverted from sources than actually ended up being used by crops. A field might effectively use only 30 or 40% of the water originally channeled toward it, with the rest lost to various forms of waste. This wasn't necessarily a problem when water was abundant and human labor was the primary limiting factor, but it did mean that irrigation could only extend agriculture a limited distance from major water sources. The further you tried to move water through open channels, the more you lost along the way, until eventually the losses made the effort impractical. There was also a hidden long-term cost of these irrigation practices that ancient farmers didn't fully understand: salinization. When irrigation water evaporates from fields, it leaves behind dissolved salts. Over decades and centuries, these salts can accumulate in soil to levels that become toxic to crops. Some historians believe that declining agricultural productivity due to salinization contributed to the fall of some Mesopotamian city-states. The very irrigation practices that had made their civilization possible eventually undermined the fertility of their land. This is a sobering reminder that even ancient technologies can have environmental consequences that only become apparent over long time scales. As civilizations developed and populations grew, the limitations of surface water sources became increasingly apparent. You could only take so much water from a river before you claimed all available flow. But below the surface lies another reservoir: groundwater. The development of well-digging technology represented a crucial expansion of humanity's ability to access water. Early wells were relatively shallow, hand-dug by workers descending into the earth and removing soil and rock until they reached the water table. In regions with high water tables, wells might only need to be 10 or 20 feet deep. But in drier regions, accessing groundwater required digging much deeper, sometimes 100 feet or more. Deep well construction in the ancient world was a remarkable engineering challenge. Workers had to prevent cave-ins while digging, often lining well shafts with stone or fire brick as they went deeper. They had to manage groundwater that began seeping in as they approached the water table. And once the well was complete, they faced the challenge of lifting water from significant depths. Various technologies emerged to address this. The well sweep, similar to the shadow but designed for deeper wells. The chain-of-pot system, where a series of containers on an endless loop of rope could be pulled up continuously. And eventually more sophisticated mechanisms like the Persian wheel, where animal power could drive a continuous lifting process. The ability to tap groundwater changed agricultural possibilities dramatically. Farmers were no longer restricted to land near rivers or streams. Communities could establish themselves in areas that had good soil but lacked surface water, as long as the water table was accessible by digging. This expanded the geographic range of settled agriculture and allowed for more dispersed population patterns. In regions like parts of India and the Middle East, groundwater became the primary source for irrigation, with villages clustered around successful wells that could support the surrounding fields. However, groundwater irrigation shared many of the inefficiency problems of surface water irrigation. The water still had to be transported to fields through open channels, where evaporation and seepage took their toll. And the labor required to lift water from deep wells was considerable. This was work that consumed huge amounts of time and effort, whether performed by humans or animals. Nevertheless, groundwater access represented a critical expansion of irrigation possibilities and supported agricultural development in regions that would otherwise have been too dry for reliable farming. The colonial and industrial era brought dramatic changes to irrigation on a scale that would have been unimaginable to ancient engineers. As European powers expanded their control over territories in Asia, Africa, and the Americas, they brought both the motivation and the technological means to develop water resources on a massive scale. In British India, for example, colonial administrators oversaw the construction of one of the world's largest irrigation networks, including extensive canal systems in Punjab and other regions. These projects were partly motivated by a desire to increase agricultural productivity and tax revenue, and partly by a response to devastating famines that highlighted the vulnerability of rain-dependent agriculture. The scale of these colonial-era projects dwarfed anything attempted in the pre-industrial world. Canals hundreds of miles long were constructed, capable of carrying enormous volumes of water. Dams began to appear, initially relatively modest structures, but gradually growing in size and ambition. These dams serve multiple purposes: storing water for release during dry seasons, controlling floods, and creating reliable year-round water supplies for irrigation. The Aswan Low Dam, completed in Egypt in 1902, exemplified this new era of water control. It allowed for more regulated release of Nile water throughout the year, making multi-season cropping more feasible and reducing dependence on natural flood timing. Reservoir construction became a key feature of modern irrigation development. Unlike ancient systems that relied primarily on run-of-river water or seasonal floods, reservoirs could capture water during times of plenty and store it for times of scarcity. This smoothing out of seasonal variation in water availability had profound agricultural implications. Farmers could grow crops during dry seasons, potentially harvesting 2 or even 3 crops per year instead of 1. Land that was previously cultivable only during certain months could become productive year-round. The economic implications were enormous. The same piece of land could now generate multiple times the annual output. But these large-scale irrigation projects also came with significant social and environmental costs that weren't always anticipated or addressed. Dam construction often required displacing populations from areas that would be flooded by reservoirs. The alteration of natural river flow patterns affected ecosystems, fish populations, and downstream communities that had adapted to historical water patterns. Increased irrigation led to rising groundwater levels in some areas, causing waterlogging and salinization problems. The complexity of managing these large systems created new challenges in water allocation, maintenance, and governance. Who would decide which regions received water during shortages? How would the costs of system maintenance be distributed? These questions sometimes led to conflicts that persist to this day. The introduction of mechanical power to water movement represents one of the most transformative developments in irrigation history. For thousands of years, moving water against gravity required human or animal muscle power. This fundamental limitation constrained how much land could be irrigated and how reliably water could be delivered. The development of pumps changed everything. Early pumps were often steam-powered, burning coal, or wood-to-drive mechanisms that could lift far more water with far less labor than any previous technology. A single steam pump could do the work of dozens of laborers or several animals, operating continuously without rest. As internal combustion engines and electric motors became available in the late 19th and early 20th centuries, pumping technology became more accessible and affordable for individual farmers rather than only large estates or government projects. A farmer with a small diesel or gasoline engine could pump water from a well or river to fields that were higher in elevation or distant from the water source. This democratization of pumping power contributed to a massive expansion of irrigated agriculture. Land that had been considered marginal or unsuitable for farming could now be brought into production. Groundwater resources that were too deep to access with hand-dug wells and manual lifting could now be tapped with drilled wells and motorized pumps. The ability to move water under pressure, not just through gravity-fed channels, opened up entirely new approaches to irrigation. Pressurized systems could deliver water through enclosed pipes rather than open channels, dramatically reducing evaporation losses. Water could be moved uphill, allowing for irrigation of terrain that gravity-based systems couldn't reach. Distribution could be more precisely controlled, with valves and flow meters allowing farmers to apply specific amounts of water to specific areas. This represented a fundamental shift from passive irrigation systems that worked with natural water movement to active systems that could impose human will on water distribution regardless of topography or natural flow patterns. However, mechanized pumping also introduced new dependencies and vulnerabilities. Farmers now needed fuel or electricity to operate their irrigation systems, creating ongoing costs that hadn't existed with gravity-fed systems. Mechanical equipment required maintenance and eventual replacement. Pumping from groundwater sources at rates faster than natural recharge could deplete aquifers, causing water tables to drop and requiring ever deeper wells and more powerful pumps, a potentially unsustainable cycle. In many regions around the world today, groundwater depletion driven by irrigation pumping represents a serious long-term threat to agricultural sustainability. The same technology that enabled massive expansion of irrigation also created the possibility of overexploiting water resources in ways that previous generations of farmers physically couldn't. The development of sprinkler irrigation represented a conceptual breakthrough in how we think about delivering water to crops. Instead of flooding fields or channeling water along furrows, sprinkler systems attempt to mimic natural rainfall, distributing water through the air in small droplets that fall onto crops and soil. The basic concept isn't particularly new. Some form of sprinkler irrigation has existed for over a century, but the technology has evolved dramatically over time. Early sprinkler systems were relatively simple, using perforated pipes to spray water across fields. They were more efficient than flood irrigation because they reduced runoff and could be controlled more precisely, but they still required significant labor to move pipes and set up equipment. The real revolution in sprinkler irrigation came with the development of mechanized systems that could automatically move across fields while operating. Center pivot irrigation, invented in the 1940s and becoming widespread from the 1960s onward, exemplifies this advancement. These systems consist of a long lateral pipe supported by wheeled towers, rotating around a central pivot point and watering a circular area that can encompass hundreds of acres. The visual signature of center pivot irrigation, those distinctive green circles visible from aircraft or satellite imagery in arid regions, has become synonymous with modern industrialized agriculture in places like the American Great Plains, the Middle East, and parts of Africa. Sprinkler irrigation offers several advantages over traditional surface irrigation methods. Water application can be much more uniform, with each part of the field receiving approximately the same amount of water, rather than some areas being overwatered while others receive too little. The amount of water applied can be precisely controlled and metered. Fertilizers and other agricultural chemicals can be injected into irrigation water and delivered directly to crops through the system, a practice called fertigation. Labor requirements are dramatically reduced compared to moving irrigation pipes manually or managing surface water flow through fields. But sprinkler systems also have limitations and costs. They require significant capital investment. A large center pivot system can cost hundreds of thousands of dollars. They consume energy to pressurize water and move the equipment. In windy conditions, water distribution can become uneven, with droplets blown off course. Evaporation losses can be significant, particularly in hot, dry, windy conditions where fine water droplets evaporate before reaching the ground. Some crops are sensitive to having wet foliage and can develop disease problems when irrigated with sprinklers rather than surface methods. And sprinkler systems are generally not suitable for all terrains. They work best on relatively flat land without significant obstacles. Despite these limitations, sprinkler irrigation represented a major step forward in irrigation efficiency and helped enable agricultural production in regions where water scarcity made older, less efficient methods impractical. The ability to apply water in controlled amounts on flexible schedules, matching crop needs rather than being constrained by fixed irrigation cycles, gave farmers much more management control. This precision in water application will become even more important as water resources became increasingly stressed and the need to maximize productivity per unit of water intensified, a challenge that continues to drive irrigation innovation today. The evolution of irrigation took another revolutionary leap forward with the development of drip irrigation, a technology so elegantly simple in concept yet so profound in impact that it fundamentally changed our understanding of how to deliver water to plants. Unlike sprinkler systems that spray water through the air or traditional methods that flood soil surfaces, drip irrigation delivers water directly to the root zone of plants through a network of tubes, pipes, and emitters. Small amounts of water are released slowly and precisely right where plants need it most, drop by drop, hence the name. The modern drip irrigation system as we know it was largely developed in Israel during the 1960s, born out of necessity in a country where water scarcity wasn't just an agricultural challenge, but a matter of national survival. Israeli engineer Simcha Blas observed that a large tree near a leaking water pipe connection was thriving while surrounding vegetation struggled, and he recognized that the slow, steady drip of water was more effective than occasional heavy watering. This observation led to the development of the first practical drip irrigation systems, which Israel began deploying widely across its agricultural sector. The results were remarkable. Crops grew better with less water, sometimes dramatically less. What makes drip irrigation so efficient is that it minimizes or eliminates most of the major sources of water loss that plague other irrigation methods. Because water is delivered through enclosed tubes rather than open channels, evaporation losses during transport are nearly zero. Because water is applied directly to the soil surface or even below it, evaporation from the soil surface is minimized. Because application rates are slow and controlled, runoff is virtually eliminated. The soil has time to absorb the water rather than having excess flow away. And because water is delivered precisely where plant roots can access it, there's no waste from watering bare soil between plants or areas without crops. The efficiency gains from drip irrigation compared to traditional methods can be staggering. While flood irrigation might be only 30 to 40% efficient, meaning 60 to 70% of water is lost to various forms of waste, a well-designed drip system can achieve 90% efficiency or higher. In practical terms, this means that the same crop can be grown with half or even less than half the water. For farmers in water-scarce regions, this isn't just about saving money on water costs. It's about making agriculture possible at all, or about bringing additional land into production with existing water supplies. Beyond water efficiency, drip irrigation offers other significant benefits. Because water is applied directly to roots rather than wetting foliage, many plant diseases that thrive in moist leaf conditions are reduced. Weed growth between crop rows is suppressed because only the soil near crop plants receives water. Fertilizers can be applied to the drip system in precisely controlled amounts and timing, a practice called fertigation that allows for much more efficient nutrient delivery than broadcasting fertilizer across fields where it might wash away or be unavailable to plant roots. The ability to apply small, frequent amounts of water means that soil moisture can be maintained in an optimal range rather than cycling between waterlogged and dry conditions. However, drip irrigation isn't without challenges and limitations. The initial investment is substantial. Installing a comprehensive drip system with all necessary components can cost significantly more per acre than simpler irrigation methods. The emitters that release water drop by drop can become clogged by particles in water, by mineral deposits, or by biological growth, require infiltration systems and regular maintenance. The plastic tubing has a limited lifespan and must eventually be replaced. The system requires some technical knowledge to design, install, and operate effectively, and drip irrigation is most suitable for row crops and orchard situations where permanent installations make sense. It's less practical for situations where field use changes frequently or where crops are densely planted in ways that make laying irrigation lines difficult. Despite these challenges, drip irrigation has expanded dramatically since its introduction, particularly in regions facing water stress. California, facing chronic water shortages, has seen massive adoption of drip irrigation for high-value crops like grapes, almonds, and vegetables. Australia has similarly embraced the technology. Throughout the Middle East and North Africa, drip irrigation has enabled agricultural production in extremely arid conditions, and the technology continues to evolve, with new emitter designs that resist clogging better, subsurface drip systems that place water delivery lines below ground where they're protected from damage and evaporation, and control systems that automate operation based on plant needs. The adoption of drip irrigation coincided with and helped drive a fundamental shift in how we think about water use in agriculture. For most of history, the prevailing assumption was simple. More water means more crop growth and higher yields. Farmers tended to apply generous amounts of water, reasoning that plants could always use more and that it was better to err on the side of too much rather than too little. This made sense in a world where water was generally abundant and the costs of over-irrigation weren't well understood. But as water resources became strained and competition for water intensified, this approach became unsustainable. The concept of water use efficiency, getting maximum crop production from minimum water input, emerged as a crucial metric for modern agriculture. Researchers began carefully measuring not just how much water was applied to fields, but how much of that water actually contributed to crop growth versus being lost to waste. They discovered that there's often an optimal water application rate that maximizes production per unit of water used, and that applying more water beyond this point yields diminishing returns or even reduces productivity. Plants can be stressed by too much water just as they can by too little, with waterlogged soil causing root oxygen deprivation and creating conditions for root diseases. This shift toward precision in water management required new ways of measuring and monitoring, instead of simply running irrigation on fixed schedules or based on visual observation of crops. Farmers needed to know what was actually happening in the soil and what crops actually needed at any given time. This is where sensor technology entered the picture, transforming irrigation from an art based largely on experience and intuition to a science based on real-time data. Soil moisture sensors became a critical tool, providing objective measurements of how much water is present in the root zone where it actually matters to crops. Modern soil moisture sensors use various technologies to measure water content. Some rely on electrical resistance, which changes as soil moisture varies. Others use capacitance, measuring the dielectric properties of soil that shift with water content. More sophisticated sensors use time domain reflectometry, sending electromagnetic pulses through the soil and measuring how they're affected by moisture. These sensors can be installed at multiple depths to understand the moisture profile throughout the root zone, providing a detailed picture of water distribution. The data they provide allows farmers to make informed decisions about when to irrigate and how much water to apply, replacing guesswork with evidence. Automated control systems took this concept further by not just measuring conditions, but acting on the measurements. Timers could turn irrigation systems on and off according to program schedules, but smart controllers could modify those schedules based on sensor inputs. If soil moisture sensors indicated adequate water, irrigation could be delayed or skipped. If sensors showed dry conditions developing, irrigation could be triggered automatically. This automation meant that irrigation could respond to actual crop needs rather than running on rigid calendars that might apply water when it wasn't needed or fail to provide water when it was. The integration of sensors, controllers, and irrigation systems created what we now call precision irrigation, the ability to apply the right amount of water at the right time to specific zones within a field based on real-time conditions. This represents a dramatic departure from traditional uniform irrigation that treated entire fields as homogeneous units. Modern precision systems recognize that different areas of a field might have different soil types, different drainage characteristics, or different crop needs, and they can vary water application accordingly. Variable rate irrigation systems on center pivots, for example, can adjust water application as the system rotates, delivering more water to areas that need it and less to areas that don't. The next evolution in irrigation management came with the integration of external data sources and computational models to inform irrigation decisions. Weather data became a crucial input. Knowing temperature, humidity, wind speed, and solar radiation allows for calculation of evapotranspiration, the combined water loss from soil evaporation and plant transpiration. Evapotranspiration represents the fundamental water demand that irrigation must replace. And being able to calculate it precisely means being able to match irrigation supply to actual plant water use. Historical weather data, current conditions, and weather forecasts can all feed into irrigation scheduling decisions. Evapotranspiration calculation isn't simple. It requires understanding plant physiology, growth stages, and how various weather factors interact to drive water loss. Fortunately, researchers have developed standardized methods for calculating reference evapotranspiration and crop coefficients that adjust for specific crop types and growth stages. These calculations, which once required significant manual effort and expertise, can now be automated through software and online services that pull in weather data, apply the appropriate formulas, and generate irrigation recommendations. Farmers can access these tools through web platforms or smartphone apps, bringing sophisticated agricultural science to routine daily decision-making. Artificial intelligence and machine learning are now entering the irrigation management picture, taking data-driven decision-making to another level. AI systems can analyze vast amounts of historical data on weather, soil conditions, crop growth, irrigation applications, and yields to identify patterns and relationships that aren't obvious to human observers. They can learn what irrigation strategies produce the best outcomes under various conditions and generate recommendations that optimize for multiple goals simultaneously, maybe maximizing yield, minimizing water use, reducing energy costs, and managing disease risk all at once. These systems can adapt and improve over time as they accumulate more data and observe the results of their recommendations. Some advanced AI-driven irrigation platforms now integrate satellite imagery and drone data, using visual analysis of crop health and growth to inform irrigation decisions. Multispectral imaging can detect plant stress before it's visible to human eye, allowing for early intervention. Thermal imaging can identify areas of a field where crops are experiencing water stress by detecting temperature differences that indicate reduced transpiration. This remote sensing capability means that large farming operations can monitor fields that would be impractical to inspect physically on a regular basis, identifying problems early and responding with precision. The shift toward controlled environment agriculture has introduced entirely different approaches to water management that challenge traditional assumptions about how crops must be grown. Hydroponic systems, where plants grow with roots suspended in nutrient solution rather than soil, represent a fundamental departure from millennia of soil-based agriculture. In these systems, plants receive all their water and nutrients from carefully formulated liquid solutions that are delivered directly to roots. There's no soil to hold water or nutrients, no natural buffering of conditions. Everything must be precisely controlled and monitored. Nutrient film technique, or NFT, takes hydroponics to an extreme of efficiency. In NFT systems, a thin film of nutrient solution flows continuously along channels where plant roots are positioned, providing constant access to water and nutrients while keeping roots mostly exposed to air for oxygen access. These systems use remarkably little water compared to soil-based agriculture, often 10 times less or more. The water that isn't immediately taken up by plants isn't lost to seepage or evaporation. It flows back to a reservoir where it can be recirculated. This represents a fundamentally different water paradigm than traditional irrigation. Comparing water use between soil-based and soilless systems reveals dramatic differences in efficiency. A conventional field-grown tomato crop might require thousands of gallons of water per plant over a growing season, with most of that water being lost to soil evaporation, deep percolation beyond root zones, or maintaining adequate soil moisture around roots. The same tomato plant in a well-managed hydroponic system might use a tenth of that water or less, with virtually all water either taken up by the plant or recirculated for continued use. This efficiency has profound implications for agriculture in water-scarce regions or in situations where water costs are high. However, it's important to understand that these soilless systems aren't universally superior. They're highly efficient, but they require controlled environments, significant infrastructure, technical expertise, and ongoing management. They're economically viable for high-value crops where the premium quality or out-of-season production justifies the costs, but they're not practical replacements for bulk commodity crop production in many situations. Wheat, corn, rice, and other staple crops that feed billions of people are still predominantly grown in soil with conventional or improved irrigation methods, and that's likely to remain the case for the foreseeable future. The value of soilless systems lies not in replacing all agriculture, but in providing highly efficient alternatives for specific applications. The concept of closed-loop water systems takes efficiency even further by essentially eliminating water waste through continuous recirculation and reuse. In a truly closed system, water is captured after use, filtered and treated as necessary, and returned to the growing system. Water leaves the cycle only through plant uptake and transpiration, or through minor losses like evaporation from plant surfaces. Some advanced greenhouse operations achieve water use rates that are a fraction of what even drip irrigation in open fields requires, by combining soilless growing methods with closed-loop recirculation and environmental controls that minimize transpiration rates. These closed-loop systems require careful management of water quality because water that's continuously recirculated can accumulate salts, pathogens, or other contaminants. Advanced filtration, UV sterilization, and periodic water quality testing become essential. Some operations use reverse osmosis or other treatment technologies to maintain optimal water quality. The complexity and cost of these systems mean they're currently limited to high-value applications, but they demonstrate what's possible when water efficiency is pursued to its logical conclusion. In regions facing severe water scarcity or in future scenarios like space agriculture, where every drop must be conserved, these ultra-efficient approaches may become not just desirable but necessary. The drive toward ever greater irrigation efficiency isn't just about technological capability. It's increasingly about necessity. Water scarcity is intensifying in many of the world's most important agricultural regions. Aquifers that accumulated over thousands of years are being depleted in decades. Rivers that historically flowed year-round now run dry for parts of the year due to irrigation withdrawals. Competition for water between agriculture, urban use, industry, and environmental needs is creating conflicts and forcing difficult allocation decisions. Climate change is altering precipitation patterns, bringing more drought to some regions while causing flooding in others, and making historical patterns less reliable for planning. In California's Central Valley, one of the world's most productive agricultural regions, groundwater levels have dropped dramatically due to irrigation pumping during recent droughts, causing land subsidence, well failures, and long-term sustainability concerns. In India, where groundwater supports irrigation for hundreds of millions of people, water tables are falling at alarming rates in many regions. The Colorado River in the western United States, which provides irrigation water for millions of acres, is so heavily used that it often fails to reach the ocean. The Aral Sea in Central Asia has shrunk to a fraction of its former size due to irrigation withdrawal from rivers that once fed it, creating an ecological disaster. These examples illustrate that irrigation, for all its benefits, is not without serious environmental costs when practiced unsustainably. Climate change adds additional pressure and uncertainty to water management. As temperatures rise, evapotranspiration rates increase, meaning crops need more water even if precipitation doesn't decline. Changes in precipitation patterns may bring rain at times when it's less useful for agriculture, while causing drought during critical growing periods. Snowpack in mountain regions that has historically provided natural water storage, releasing meltwater gradually through spring and summer, is declining in many areas, changing the seasonal availability of irrigation water. Extreme weather events, severe droughts followed by intense floods, are becoming more common in many regions, challenging water management systems designed around historical averages. These pressures mean that irrigation innovation is no longer just about improving farm economics or increasing production. It's about maintaining agricultural viability in the face of growing constraints. Regions that continue using inefficient irrigation methods may find themselves unable to sustain agriculture as water becomes scarcer and more expensive. Technologies and practices that once seemed like expensive luxuries, drip irrigation, precision sensors, advanced scheduling, are becoming necessities for survival in increasingly water-stressed environments. The farms and regions that adapt most effectively to this new reality will have competitive advantages, while those that don't may face declining productivity or even abandonment of agriculture. This challenge has sparked interest in bringing food production into entirely non-traditional spaces, where water can be controlled and conserved with maximum efficiency. Urban and vertical farming represent approaches to producing food in buildings, often in cities, using controlled environment agriculture and soilless growing methods. These operations can be established in warehouses, on rooftops, in shipping containers, or in purpose-built vertical farm structures, where crops are grown in stacked layers under LED lighting with precisely controlled temperature, humidity, and nutrients. The water efficiency of these systems can be extraordinary. Because they operate in enclosed environments where humidity can be controlled, transpiration rates can be managed to minimize water loss. Because they use soilless methods with recirculation, water that isn't taken up by plants is captured and reused. Some vertical farms claim water use rates that are over 95% lower than conventional field agriculture for the same crops. They can also produce crops year-round regardless of outdoor weather conditions, achieving much higher annual productivity per square foot of growing area than traditional farming. However, urban and vertical farming face significant economic challenges that currently limit widespread adoption. The infrastructure costs are substantial. Building a climate control facility with artificial lighting and automated systems requires major capital investment. Energy costs for lighting, climate control, and water circulation can be significant, especially if renewable energy isn't available. These systems are economically viable for high-value crops like leafy greens, herbs, and specialty items that can command premium prices, but they're not currently competitive for bulk commodities. The technology is improving and costs are declining, But whether these approaches can scale to contribute meaningfully to global food production remains an open question. Nevertheless, urban and vertical farming fill important niches. They can produce fresh vegetables in food deserts where access to quality produce is limited. They can supply restaurants and retailers with ultra-fresh products harvested hours before consumption rather than days or weeks. They reduce transportation costs and emissions by producing food near where it's consumed. They're not affected by droughts, floods, or other weather events that can devastate field crops. And they demonstrate approaches to agriculture that may become more important as climate change and water scarcity intensify. Even if vertical farms never produce the majority of food, they represent valuable diversification of our food production systems. The economic impact of efficient irrigation extends beyond just water savings. Farmers who adopt precision irrigation often see multiple benefits that improve their bottom line. More efficient water use means lower pumping costs. Less water to move means less energy consumed. More precise water application often leads to better crop quality and higher yields by maintaining optimal soil moisture rather than cycling through stress periods. Reduced disease pressure from keeping foliage dry or avoiding waterlogged soil conditions means lower pesticide costs and crop losses. Better nutrient management through fertigation means less fertilizer waste and lower input costs. And in regions where water availability limits how much land can be farmed, more efficient irrigation means being able to farm more acres with the same water allocation. These economic benefits create a business case for investment in irrigation technology even without regulatory pressure or water scarcity concerns. A farmer who can increase yields by 10% while cutting water use by 30% and reducing energy and input costs has improved profitability significantly. The payback period for irrigation system upgrades may be just a few years, after which the farmer enjoys ongoing cost savings and productivity gains. This economic logic is driving adoption of efficient irrigation even in regions where water is still relatively abundant, because efficiency translates directly to competitive advantage. There's also risk reduction value in efficient irrigation. Farmers with precise control over water application are less vulnerable to drought conditions because they can maintain production with less water. They're less exposed to water price volatility if water becomes more expensive. They're more likely to meet evolving environmental regulations around water use. And they're better positioned to adapt to climate change impacts on water availability. This resilience is value that may not be immediately apparent in simple payback calculations, but becomes evident during crisis periods. Looking toward the future, water management and agriculture will likely need to incorporate technologies and approaches that currently seem exotic or experimental. Desalination of seawater or brackish groundwater is already being used for irrigation in some arid coastal regions, though the energy requirements and costs remain high. As renewable energy becomes cheaper and desalination technology improves, using ocean water for agriculture may become more viable, potentially transforming coastal deserts into productive farmland. Israel has pioneered large-scale agricultural use of desalinated water, demonstrating technical feasibility. But economic scalability for widespread adoption remains challenging. Atmospheric water harvesting, extracting moisture directly from air, represents another frontier technology. Various approaches exist, from simple condensation systems to advanced materials that can capture water vapor even in relatively dry air. These systems could potentially provide irrigation water in locations where no conventional water sources exist, though current technology produces water at costs that are prohibitive for most agricultural applications. As technology advances, particularly if energy costs continue declining with renewable sources, atmospheric water harvesting might become viable for high-value crops in extremely water-scarce environments. The ultimate frontier of irrigation efficiency may be systems that approach theoretical limits of water productivity, using only the water that plants actually transpire with virtually no waste at all. This would require perfect closed-loop recirculation, precise environmental control to minimize transpiration rates while maintaining plant health, and possibly genetic modification of crops to maximize water use efficiency at the cellular level. Some researchers are exploring plants engineered to open their stomata, the pores through which transpiration occurs, only when absolutely necessary, reducing water loss while still allowing photosynthesis. Others are investigating crops that can tolerate higher salinity, potentially allowing irrigation with lower quality water that would damage conventional crops. There's also growing interest in integrating water management with other resource cycles to create more holistic, sustainable agriculture systems. Aquaponics combines fish farming with hydroponic crop production, using fish waste as a nutrient source for plants while plants help clean water for fish, a closed-loop system that produces both protein and vegetables with minimal water use. Agroforestry approaches that combine trees with crops can modify microclimates to reduce water stress and improve water retention in soil. Regenerative agriculture practices that build soil organic matter improve water holding capacity, reducing irrigation needs. These integrated approaches recognize that water management can't be optimized in isolation, but must be considered as part of complex agricultural ecosystems. The story of irrigation from ancient canals to AI-driven precision systems is ultimately a story about human ingenuity, responding to fundamental challenges and constraints. Each era developed approaches appropriate to its circumstances. Ancient farmers with simple tools and abundant land maximized labor efficiency. Industrial agriculture with mechanization and ample water maximized production. And modern farmers facing scarcity are maximizing water productivity. We're now in a transition period where the assumptions that guided agricultural water use for generations are being fundamentally questioned and revised. The future of irrigation will be defined not just by technological sophistication, but by our ability to use water wisely in a world where this essential resource can no longer be taken for granted.